Hi guys, this is Professor Darwish with you again, and in this session I would like to talk about Euler's theorem as well as Euler-Twotiant function phi. So we'll begin with discussing the phi function or the totient functions. So this is Euler's theorem, and of course we will talk about the totient functions. And we refer to it as the Greek letter phi or phi of n. Now, of course, we'll start with the totient function. So we state that a phi of 1, or we start by saying the totient function of 1 is equal to 1. Now, what does it mean? This is what it means, definition. In order for us to evaluate what's the phi, so the phi function or the totient function represent or is the number. It's a number. It's an integer number, of course. It's the number of positive integer that are less than another positive integer n, but there's a condition. The condition is that that number, okay, is the number of positive integer or the positive integer less than n, and relatively prime to n, prime to n. Okay, to explain the definition, I will begin with an example. Let's say that we want to evaluate the totient function phi of 37. Okay, so let's find out. So first of all, 37 is an integer. So this is an integer. Okay, and we're talking about positive integers, so this is a positive integer. It's positive integer, and we are going to calculate or evaluate all the numbers that are less. So we want to find out all the numbers that are less than 37 and relatively a prime to 37. So basically we are going to start again. We can't start with 37, it has to be less than 37. So less than 37, so we begin with 36, and then 35, then 34, and we will continue all the way to 1. So 36 is, of course, is less than 37. Now, is 36 and 37 are relatively prime? Now, the meaning of relatively prime is that the GCD we talked about before, the greatest common divisor, GCD between 36 and 37, when they are relatively prime, we want to check that this is equal to 1. So this is the condition. This is the actual condition. So when the GCD between these two numbers means that the greatest common divisor, the greatest number that divides both of them, is only 1. Okay? Now, obviously, 36 and 37, the only common divisor between them is 1. Now, the same thing applies to 35. 35 and 37 is 1, and GCD to 34 and 37 is 1. And actually, if you perform this all the way to 1, so then you find out the GCD between 1 and 37, obviously this is 1. Okay, so when you count this, it will be 36. So in this case, the answer, the phi function of 37 is 36. Now, of course, if you take a deep look at 37, and you'll find out that 37 is a prime. It's only divisible by itself and 1, so it's prime. So then we can really come up with the formula. So if we are looking for finding the totient function for the prime number p, then it's equal to p minus 1. So like in our example, 37 minus 1 is 36. So this is going to be the formula, very important, powerful formula. All right, and of course, remember that when you perform the GCD with all the numbers with respect to the prime, obviously they are going to be relatively prime. Okay, so this is the proof here, or indirect proof, but that's. Now another example. All right, so let's say example 2. This is one here. Example 2. Let's say again Q of 35. I'll come back to 35. Q of which one is prime? Okay, 36 is not prime, 35 is not prime, is divisible by 5. The 34 is not prime, 33 is not prime because it's divisible by 11. Then 31 is a prime. So 31 is a prime, so the answer will be 30 here. Okay, p minus 1, it will be 30. Okay, so 31 is not divisible by any number except itself and 1. Okay, so that's why. Now let's take a look at another example that is not a prime. So let's take a look at this example of 35, because I was looking at 35. Now obviously 35 is not prime. So what's the idea? The idea is to find all the numbers less than 35. So starting from 34, okay, and you go all the way down to you start from 34, then 33, and 32, and find out if this condition GCD between the number, which is, of course, we start with 34 and 35. You double check if this is equal to 1. Of course, you do it with 33 and 35, and you continue all the way down to 1 and 35. And obviously, you know, there is a long series of different numbers that fits this condition. And as a matter of fact, the answer to this one will be equal to 24. Okay, so the answer, it will be 24. Now I'll show you how quickly you can find out this, all right, and how you can perform the totient function, all right, and quickly, even though 35 is not a prime. So by looking at 35 itself, it's a multiplication of uh, 7 times 5. So as a matter of fact, so if you look at the factors of 35, one of the factors, okay, of course, you know, there's 35 times 1, and there is the other factor is 5 and 7. Okay, I don't see any other factor, the different factors. So we have 5 and 7. These are the factors for 35. So we can state, we can represent this equation, this function 35, in terms of the phi function of 5 times multiplied by phi function of 7. So these are the factors. Now notice that here, I'm going to change the color. Notice that this is a prime, 5 is a prime, and 7 is a prime. Now obviously we can apply the equation. Let's call it equation number 1. So from 1 we can say that the number of, to find all the numbers or all the positive integers that's less than 5 and they are relatively prime with 5. So obviously this is going to be 5 minus 1. So because it's p minus 1, so it is 5 minus 1, which is 4 times, this is 7. Also 7 is a prime, 7 minus 1. Now which is, of course, the answer here is 4 times 6, and this will give us 24. Notice that this is the result and this is the result. So if you want to go all the way, perform this one to verify it, you can do the same thing. Okay, excellent. So in general, if the multiplication for if there are two numbers that are prime, so again in general here, if you have n, which is equal to two different prime, p and q are prime, okay, are prime, so the phi of n, okay, which is n is the multiplication of p and q, is, so the totient function of n is equal to p minus 1 times q minus 1. And of course, you know, this is utilized in cryptography and RSA cryptography. So we use this one, we use the totient function in application like cryptography, and specifically it's Raven, Shamir, Edelman, public key, private key, public key cryptography. Okay, so this is about the totient function. So now let's move on, because I'm going to talk about Euler's theorem. So I'm going to go to the next page, and then I'll talk about Euler's theorem. And this is Euler's theorem. Euler's theorem that for every a and n that are, so both are integer, that are relatively prime, So both, this is an integer, positive integers that are relatively prime. We have this formula. So the number a to the power phi of n is congruent or equivalent to 1 mod n. So this is Euler's formula. As you can see, it depends in the totient or the phi function. Okay, now an example. Now let's say that we picked up two numbers that are, they should be relatively prime. They don't have to be prime themselves. They don't have to be prime. So they don't have, again here, they don't have to be prime, okay, themselves. Okay, so the example, let's say that we have chosen a to be 3. Yeah, 3 is a prime, but we have chosen n to be 10. 10 is not a prime. Okay, so let's apply this equation. So first of all, we need to check that the GCD between 3 and 10 is equal to 1. Now, because this is the condition, they need to be relatively prime. The two numbers 3 and 10, are they relatively prime? So is the greatest common divisor between 3 and 10 is 1? Yes, in fact it is true. So the condition applies. So then we can express this one as according to the formula. So we can say 3 to the power phi of n, n is 10, is congruent to 1 mod 10. Now, so here, in order to complete this one, we have to compute. Okay, so here we have to evaluate phi or phi of 10, which is, we need to find the number of integers less than 10, and they are relatively prime with 10. Now again, as we learned from previous examples, so we can express this one as phi of 2 times phi of 5. Now we have two primes. 2 and 5 are primes, so we can say that phi of 10 is equal to 2 minus 1, which is 1, times 4, which is equal, there are 4 integers. Okay, and as a matter of fact, if you want to find them, those integers specifically, okay, that is relatively prime, so it has to be less than 10. So relatively prime with 10, so number 9 is one of them. And is 8 and 10 relatively prime? No. 7, yes. Then 6, no. 5, no. 4, no. 3, yes. And of course 1. So obviously here phi of 10, we found it to be 4, so this will be 3 to the power 4, congruent, equivalent to 1 mod 10. Now of course, you can verify it. 3 to the power 4 is 81. Okay, so this is 81. You divide 81 by 10, the remainder is 1. So let's take another example on this. So let's say example 2. So again, let's choose a is equal to 2 and n is equal to 11. Now probably you can notice that 11 is a prime and 2 actually is a prime, so both of them in this case is a prime. But let's apply let's find first the phi of n, which is phi of 11. Now 11 is a prime, so it will be 11 minus 1, which is 10. So we already know the phi of n. So let's apply the formula. Again, 2 and 11 are relatively prime. So this is a condition. So they are relatively prime. So the condition above applies. So a and n that are relatively prime. Here a and n are relatively prime. So we find the phi function, and then we can express it as a which is 2 to the power phi function, which is 10, is equal to 1 mod n, which is 11. Okay, now this is what we have come up with. So 2 to the power 10, and of course, this will be useful in modular arithmetic. Okay, so this is the results. Now another expansion to the theorem. Okay, so for the theorem, actually here, if you multiply both sides by a, so if you multiply both sides by a, so this is the another variation for the theorem or formula. So multiply equation 1 by a for both sides. So we'll have a to the power phi of n, okay, plus 1, because we have multiplying by so because a to the power 1, which is when you add the exponent, is equivalent to a mod n. So this is the variation to the formula, like what we did with Fermat's theorem. So these are the formula. In this case, we were able to apply Euler's formula or Euler's theorem. This is Euler's theorem. Totient function, we talked about it. Okay, and we defined it as a number of positive integers that is less than n and relatively prime to n. And we made the evaluation. Then we talked about Euler's formula, which is a and n could be n integers, positive integers that are relatively prime. Means that the GCD between both is equal to 1. Okay, so there is the only common divisor between them is 1. So this is the formula, and this is the other formula. So guys, I'll see you in the next video. Have a good day, and let me close this video. Thank you.